He asked me to talk about AI use cases, and from the survey at the beginning, I understand there's quite a mixture of interest and skill level and interest. So I hope I have a little bit for everyone here. Okay. This is my agenda, and I think it's actually, I got lucky. I might actually have the right level of detail here. So at first I'm going to talk about why is everyone talking about artificial intelligence now? Okay, and I will also try to explain a little bit at a higher level, what does it entail to do AI, and most importantly, what are the common use cases that you hear in the news every single day? Okay, but from IBM perspectives, of course, we are interested in why is AI important in the enterprise. Okay. I'm more on the implementation side, so I do want to spend some time pointing out the right tools that IBM has, but also the open source community provides in order to implement artificial intelligence in enterprise applications. And then I have a couple of points at the end. Feel free to interrupt me at any time if you have any questions. Let's try to keep that interactive as much as possible. Okay, so if you got up on a Saturday morning, then you're definitely highly motivated, and I think you made a very good choice. Because AI, Enderuten is one of the names that you should definitely remember. And most of the people hopefully heard the name before. He's one of the the creators of this revival of artificial intelligence. And in 2017, he actually pointed out he's a professor at Stanford, and he used to be the chief data scientist at Baidu until a year or so ago. And he posted that on Twitter saying, Stanford's first day of class, record-breaking 1,000 people already enrolled. Okay, that was 2017. Same thing at MIT. The enrollment from 16 to 17 doubled. Okay. So there's definitely, in terms of education, there's this big movement for people wanting and needing to learn AI skills. Okay. I will not try to give you a definition of AI because I will probably badly fail, and there isn't a single definition of it. But at a higher level, you still need to have a little sense of orientation of how that all comes together. If you bear with me and say, there's cognitive applications out there, okay. Any kind of intelligence that people try to put into software, okay. Where does that come from? Okay. It comes from, people have heard of machine learning before, okay, and machine learning is really, you train a model and then you put it into your application and you make it do smart things in terms of predictions, in terms of prescription, descriptive, and so forth. And I always look at it, deep learning is part of machine learning. It's actually the math around deep learning, it goes back to the 50s and 60s. That's when it was all created, but it could never be executed. And I will try to explain to you why did it come back in the past, let's say 5 to 10 years. Okay, what were the changing trends to enable that? Okay, and so that's what I like to call, when I say AI, I really mean machine learning and deep learning. Okay, and that is in the enterprise and broader realm of advanced analytics that has a lot of data processing capabilities in it. But the most important part is the blue part. Nothing works without data. Okay, you have to have data, and if you don't have a good data platform, then you're toasted. You have to stick with me for a little bit and do some math first. Okay, so if you think of a deep learning architecture, okay, people always show those network layers. Okay, on the left side you have like an input layer, and here's the output layer, and in between you have those hidden layers, and those layers are defined by the neurons. And then you have a lot of errors, and there's different kinds of layers for like recurrent layers, convolutional layers, LSTMs, and so forth. And training a neural network is very compute intensive, and I want to get point across to you why that is the case. Okay, so you have to feed in the data, and the purpose of training the neural network is that you want to compute or train or learn a function, okay, that is a series of those linear transformations of the input to the target output. And And that is an iterative process. So you feed it the input data, you go through the flow here, and then you have this, that's what they call the forward propagation, and then you have the back propagations here, where you take the errors, okay, and update the weights, and then you do another round of iteration. The point here is that given that input data, let's say X, you want to do some image classification, and you have a label, let's call Y for it. You want to train your weights, okay, and the biases in order to be able to predict the label. So that's what you want to train for. Okay, so you want to run those weights here in order to satisfy that function, and then you have an optimization goal, so you always have like a loss function that you want to typically minimize. Okay, and that's really what it is. And there's a set of different terminology that I want to introduce. So X is typically like the data, Y is typically the labels, and W is the weights, and you have different activation functions in there. Those activation functions are nonlinear functions, sigmoid, tanh, and those are the popular functions, and those are typically very, very compute intensive. So this is where also the single precision, double precision math comes into the picture, where you need a lot of compute. Okay? And as you can imagine, okay, I have 2 hidden layers. People are talking about 1,000 layers. Okay? If you have 1,000 layers with thousands of neurons in between, for each one of those things you have to do those expensive math operations. That's where the compute, hits the fan, and that's where the beautiful GPUs, the 27,000 GPUs will come into the picture. Yes?
Are you going to share this presentation?
Yes.
Sure.
Yes. Even the video tape.
Okay, so...
We should have a video of the audience.
Yeah, I took.
Thank you.
Okay, so why deep learning now? So now that we have a rough idea, you have your input layers, your hidden layers, you have your neurons, you have your activation functions, and blah, blah, blah. So, and all of that math was invented in the 50s and 60s. Okay. So why is it coming back now? Okay. So I have 4 slides on that topic here, and bear with me. In the old days, it doesn't really matter too much. Deep learning did not make such a big difference. Okay, things are different now, and the reason is the following: we have, if you look at this graph here on the Y, on the X, you have the amount of data. In the old days, people had little data. Okay, the performance, not in compute performance, but in terms of accuracy, it did not make that much of a difference if you have small data. However, and it's always the case for the traditional machine learning models, the more data you feed in, eventually, in terms of accuracy, it just plateaued. Okay. However, if you have more data and you train your small neural models on it, or even medium or even larger models, your accuracy improves. Okay. So the efficacy of larger models will give you better model performance. That is very important. And that is enabled today because people do have more data at their hands. And here's the evidence, okay, especially for the new data types, which are images, video, text. This is where a lot of the deep learning models really shine. There's a lot of benchmarks publicly available on open source that you can go and grab and train your models on. However, bigger is not always bigger, also means more expensive, okay? And if you look at the necessary compute power in order to train all those models, 20,000 GPUs, let's assume a V100 costs $10,000. Do your math how expensive that is. Okay? It's non-trivial. But it's also the case, the larger your model, the compute necessary to train the models also needs to grow significantly. Okay. So if you look at this image recognition benchmark, in 2012 there's this AlexNet, and in 2015 there's a ResNet, maybe that was ResNet 52, I don't remember. The model size grew by a factor of 16x. Okay, and for the speech recognition, the training, the number of floating point operations, it grew by a factor of 10. Okay, so you have to also, not just more data, you also have to bring in much more compute power in order to train your models. Okay. This one here is a B100, and I think the Summit they have B100s in there. What happened now? Okay. The last point is there is really good success stories out there now for deep learning. Okay, and again for the new data types such as image. So ImageNet is one of the classic benchmarks for image recognition. In 2010, people had shallow networks. The accuracy was the error rate. It was not very good. Okay, but then people started to add more and more layers, okay, to the network, which makes it much more compute intensive. Okay, but it also brought down the error rate. Okay, and now the error rate is actually, in some cases, better than the people, the humans doing the work for the image recognition. But at the same time, the compute went up by a factor of 10. Okay, so keep that in mind. So this is why deep learning has kind of this revival: more data, more compute, okay, and deeper neural models, which requires all of that. You need more training data, and you do need more compute power. Same thing with speech recognition. Here's the time. It's kind of plateaued since 2010, and once the deep learning models came along again, improving the error rate as the accuracy actually was only possible with those models. All right, so
So in terms of industries, I
yes.
think all the industries started using, but where you think in unique industries where AI is more popular?
It's the slide after that one.
Oh, okay.
Okay. It depends on which industry you're also in. That, of course, the industries that
Okay.
you're going to highlight. But I mean, this is not typically an IBM slide.
Okay,
But
okay,
those are like the kind of the popular, the specialized API. That's what people in the news observe. And the data types here are text or language. Okay, so there's tremendous progress in language translation. Speech to text transcription, tremendous progress there. Language understanding, knowledge graph reasoning, object detection here, or face recognition in videos. Okay, so there's tremendous progress has happened in terms of accuracy and in terms of performance in the past 5 to 10 years. Okay, so but that's like the popular AI. Let's call it that way. Nevertheless, the more critically people ask the question, are we there yet? Okay, so there's still a big however, and people may know Professor Michael Jordan from University of Berkeley, who is looking at those nice pictures a little bit more critically. Okay, no, we are not there yet. Okay, so for each one of them, if you look at computer vision, yes, we can label some objects, but in terms of common sense understanding, it's not on par with humans yet. Okay. Same thing for speech recognition. Yes, there's, I can talk something, it gets translated to text, it gets translated back to speech, and it comes out in a different language even. Okay, yes, that is possible, but still in terms of common sense understanding, we are not there yet. Okay. Same thing for NLP and robotics. So we made tremendous progress, but we are by far not there yet.
Can you give an example of that, what you just mentioned, in terms of speech recognition? When you say it's not yet possible, what is not yet possible?
The reasoning, so just being able to deal with the syntax and the tokens and the semantics of words, that's one aspect. And for that, with all the compute power, the neural models do a very good job. But in terms of common sense and understanding of scenes or plays or whatever.
So like all the assistants, right? Like Google Assistant and
Yes.
Siri.
Those are actually very...
they're pretty good, right?
They're pretty good, but also still very simple. Okay, there's
Okay.
like Siri and so forth, a lot of it is lookup. Okay, yes, there is a lot of semantics involved with it, but it's the more global common sense is still not there.
Could it be like the tone, like you ask the question, the
Oh,
person answers,
Yeah,
whether he sounds
sarcasm and
happy or he
those kind
sounds
of
sad?
things, like sentiments and so forth. Yeah, there is a lot of sentiment and all is happening, but it's still
Okay.
lacking.
You know, like with the Google Assistant, I was really amazed that it could go from one language
Mhm.
to
The
another.
different language, yes.
Right?
Yeah, that's
You know,
exactly the speech to text and text to speech in different language with the language
Right.
translation. That is, yep, pretty
I
good.
mean, it could, you know, like if I speak to it in English, it knows. And
Mhm.
you know, as long as I register beforehand and say, this is my second language,
Uh-huh.
it recognizes it immediately.
Yes.
Right?
However, in terms of what you say, so if you use a lot of sarcasm and those things,
Sarcasm,
it's
okay.
still, and sarcasm is just one of the examples that people very often quote, but there's a lot of other, contextual knowledge often missing. Okay, with the knowledge graphs, okay, so they try to pull, or knowledge bases, they try to pull in those, like Wikipedia, those global knowledge bases, they often get pulled in because they're universal. Okay, but for more enterprise-specific knowledge bases in the humanity domain or how to conduct business and so forth, it's still lacking. One of the industries, to get back to your question, where tremendous progress actually happened is in healthcare. Okay, and this is just like so. This paper down there in the archive it's actually a very good overview paper, and I suggest people go and download it if that interests you. And it's a very high-level summary because, especially in medical image analysis, there's so many different variations, and I'm not a doctor, so I barely understand any of that language even. Okay, but from what I understand, a lot of image processing happens here, and a lot of tremendous progress has been made, and in terms of state-of-the-art results being on par with doctors. Okay. So examples that you will often see are like being good at classification tasks, okay, or looking at those images and doing segmentation on it, nodule classification, looking at X-rays into different slides in X-rays and doing analysis on those. A lot of progress has been made here. Okay. And at IBM, we actually have done a lot of those experiments as well. So IBM, we have even a business unit called Watson Health, where we do a lot of medical image processing there. Okay. This is one of the examples. Catherine actually might have seen it before. So that's a slide of an X-ray, and the task was train a model on it and then do some inference to say, in terms of probability, is that a severe or a less severe or no severity at all for breast cancer. Okay. That's one of the examples. Another example here is you have this X-ray of your upper body, okay, and you just need to do image segmentation on it in order to identify where is your heart or any other organs in that image, okay, in order to take a closer look. The reason why I wanted to show those examples, although it's very high level, because if you look at the specialized or popular AI, where you hear like the VGGs and the AlexNet and the ResNet for speech and image processing and so forth, those are all very good models. Okay, but if you go into those more practical cases, like even for medical image processing, you don't hear any of those ResNets or so forth. Those are all very good. Go ahead.
Can you explain a little bit about ResNet? What is ResNet?
Oh, ResNet is one of those network architectures. Okay, you have, and there's a ResNet 50, a ResNet 101, and 152. Those numbers are the number of layers, or number of hidden layers in that architecture. Okay, And as I've shown at the very beginning, you have on the left-hand side you have the input data, and then it needs to go to a series of those layers in order to do those nonlinear transformations, okay, and in order to train your predictive function, okay, with a backpropagation and all of that. So ResNet is just a very popular neural model that I believe the Google folks developed on how to stack and what kind of network layers they stack together.
Think of it as a model,
A model.
one model,
Model.
and however the model architect, when Berthold say ResNet or whatever other name, just think of it as a
A
model.
model. Okay. Is it a software model or hardware model?
Software.
It's
Software.
software,
Okay.
architecture.
Architecture. Okay.
It's one of those neural models.
Yeah.
Thank you.
Just think model, some data coming in, something coming
Okay.
out.
Okay.
Yeah, so ResNet, AlexNet,
AlexNet.
VGG, those
Yeah.
are the
Those are all
popular
just
ones.
names.
Those are the
Yeah.
names of
Yeah.
model architectures.
I see.
Yes. If you go to Google and you search for cats and dogs, they use one of those models to
Yeah.
classify cats and dogs. Okay, so if you go into those specialized ones, you really need to be a deep learning data scientist in order to design those models. I mean, ResNet, although it's in everyone's mouth now, developing those models is extremely hard and it's time consuming. Okay? But once they're ready, people are happily using them. So here's one that I wanted to pull out here called a UNet, which is not by far not as popular, but much more useful to do this image classification. Medical image processing is much harder than identifying cats and dogs. Okay, in terms of available training data, in terms of those lines actually which you cannot see here at all. So subtle lines and shades that you see in X-rays or whatever, those are much more uncommon than what you see in pictures that you take with your iPhone. Okay, so learning those different shades here requires very specialized neural models that people have to develop. So UNet is one of them, and it does image segmentation. So it takes this medical image here and then finds all the interesting parts that doctors are looking for in that X-ray. Okay. So medical image processing, the fantastic progress there.
Why I asked is, as part of the industry, since we are in the staffing, the kind of requirements I see is more from the automobile industry also, especially on the deep learning and machine learning. So that's why, I was thinking,
Yeah,
maybe
self-driving
there is a
cars
lot
and
of demand or,
Yeah. But
they're
even like
doing more on that,
yeah.
right?
Maybe that's your slide here.
Oh, okay.
But even if you go to automotive, yes, the self-driving and the operational part,
Yeah.
that is, like the Teslas and so forth, that is one aspect of it. But
Mhm.
automotive is not only just a car and the driving of
Right.
it. There's so much more industry around it in terms of maintenance and analysis, and there's so much more to it. And even just doing your car payments, okay, on time, developing a machine learning model to predict whether somebody is able to make the next payment or not, that is also part of the automotive. It's so rich, it's
Yeah.
unbelievable, okay? And automotive is only one of them. If you look into consumer goods, you go to Amazon, you submit your reviews there, and Amazon it goes in and does NLP neural models on it to find out are people happy with that product or what do they say about it, and they use that output to improve on the product, hopefully. That's for consumer. Same thing for financial services. Automatic processing of mortgage applications, okay, or loans or whatever. And with all its complications, if you paid attention to the news lately, so people are worried about is there a lot of bias in those neural models there that discriminate, and are there is actually artificial intelligence to detect whether your artificial intelligence actually is biased or whether there's some flaws in it. So I'm not going to, but you will find it in all industries.
Right.
That's, I think, the major point that I want you to take away from this one slide here. I just want to pick a couple of more examples, not in much detail, but even if you look at banking, yes, loan applications and predictions, that is always obvious use cases, but even a lot of other use cases, if you go to your ATM and you see just a mirror there looking back, and so they actually can put a neural model in there as well, and do face detection on it to see, is that really the owner of the card, or of that card, okay? Or are they trying to, put the collar up and hide the face a little bit and still to, they stole the pin somehow, okay, and they just use somebody else's card. So put a neural model in there, do some face recognition, and it will improve. Manufacturing with robotics, that's obvious. Healthcare, I think I showed a whole bunch of examples already. That's definitely there. Finance with credit approvals, or any kind of financial product that somebody may want to. There's always automatic analysis. Can I do an upsell here or not? That's given. Same thing with personalized insurance quotes, entertainment. Actually, IBM had a whole bunch of prototypes there where we, analyzed movies, okay, and then we developed a model to automatically compose a trailer out of it, which is time-saving because that's at the end of the production, and you have only very limited time to come up with a very good trailer, and it's still time-consuming. So automating that process is definitely beneficial. Okay. Compliance is often very overlooked because it is, it has a heavy NLP part of it in it. But think of it in the following way: that a lot of companies are submitting their SEC filings, okay, and compliance would mean that we analyze also the SEC filings and do correlations and entity analysis on it in order to find out is there any fraud or that happened in terms of anti-money laundering, or there's some this guy should not be on the board because he has a conflict of interest or whatever. So all this analysis actually can be done with AI. Okay, so AI is important. That's one sentence summary. So now let's shift gears a little bit, okay? And how do you do it all? Okay, it's very simple. You just stack it with a model and you're done, and the results are great. It's not like that at all. Okay. It's very complicated. Okay. So I just want to simplify it a lot. Okay. If you accept all the use cases that we extensively went through, who is processing all those things? So I will give a couple of pointers of what are the useful tools, software tools that people are using. Okay. And because it's so compute intensive and not everyone has a summit in their basement with 27,000 GPUs. So what are other means of scaling out the compute, okay, and make it efficient? Because I'm sure in the news you heard of cases, it takes weeks, if not months, to train your model. Okay, and those statements are true. Okay, but what are workarounds? Okay. And then there's a lot of hardware acceleration happening there, with the GPUs or TPUs or FPGAs and so forth. Okay, so let's move now from here to what is the machine learning, deep learning engines. Okay. So I produced this slide, started off with copying it from datamation.com about a year or two ago, and I might have updated it a little bit. So there was this trend that almost every month, one of the large companies, they just open source their machine learning, deep learning framework. The popular tools that people, there's definitely TensorFlow in terms of deep learning, very, very popular. Same thing with Caffe, which is now Caffe 2, very heavily used at Facebook. For deep learning, there's Torch with PyTorch. From the University of Montreal, also open source now. People may have heard of H2O, which is a company, but it's also open sourced. Spark, people hopefully heard of, has MLlib in there. They have little support for deep learning, but they have a collection of machine learning algorithms built in. Deep learning for J is quite popular. Microsoft, they open sourced a whole bunch of components there. Of course, I just want to be fair here, not be biased to IBM, but there's certainly Microsoft Azure with Azure ML for machine learning. They also have deep learning in there, that's very broadly used. But then there's also very specialized toolkits there, such as the cognitive toolkit, the CNTK. There's the DMTK that they also put out. Amazon, they have MXNet that they primarily support, as well as Destiny. Baidu, they put out Paddle, also open source now. Intel, they have BigDL, for big deep learning that runs in Spark environments and so forth. But truth is that all the companies, if they, especially if they're cloud there, if you go to IBM Cloud, if you go to Microsoft Cloud, if you go to Amazon, you will find that it's not just one tool, they always make available a collection of tools. Okay? And the truth is that all those tools have strengths and weaknesses, number one, but it's also a matter of skills. Some of the developers they grew up with TensorFlow or PyTorch or whatever, and that's what they want to use, and then they just make it available. Okay? So there's no one tool that fits all the requirements, and some of them have significant overlap. And in the course of time, eventually consolidation will happen, but it did not happen yet, and so you have this plethora of tools that is available. Okay. IBM has a whole bunch of tools too. Okay. So you may have heard of IBM Watson Studio. The architecture is very similar, and we have our collection of tools. And as I said before, we do not just support TensorFlow, but we also put Caffe in there and Keras, which is a layer on top of any of those deep learning engines. But then more on the machine learning side, we have like Spark MLlib. SPSS is very popular, of course, at IBM. We also have strong support for Python with NumPy, scikit-learn, sklearn, and so forth. Those are the engines, and then you have a whole bunch of front-end authoring tools, as we call them. So there you find Jupyter notebooks, also Zeppelin notebooks that give you like a browser interface that allow you to have different kernels in there. Most popular ones are Python or was just Scala kernels that allow you to connect to some backend cluster. Okay, but we also have RStudio there and a couple of other components that allow you to connect to some data transformation engines, but also call out to the Watson APIs to do translations or sentiment analysis or compliance analysis or visual recognition. If you're a PhD student or any kind of student who wants to get into that field, okay, and you're in a research environment there, and you're inspired to become a data scientist, okay, which is what a lot of people do, then what you learn at school is extremely valuable, okay? You certainly learn a lot of optimization algorithms and schemes, okay? But if you get hired as a data scientist today, it's an extremely tough job, right? Because the expectations are very, very high. It's not enough to just know your optimization schemes and your stacking of the neural model architectures. There's also the expectation that you provide a scalable distributed implementation of it, that it runs on many different data sets, sparse and dense data sets, skewed data sets, and so forth. And it's also supposed to be optimized so it doesn't run for a week, but you can run it in 2 days or so. So today, that is a very difficult job, okay, because it's not just one role, but it's essentially 4 roles. Okay. So also slides that I've shown you here before providing those authoring tools, providing those different engines here, are trying to make the life of data scientists easier, so that they can just think of, okay, I have this super cool logistic regression algorithm that I know will give me the best precision ever. That is not enough. So you still have to put it into the system and make it scale and run fast and provide good results. So a lot of tools are working in that realm. We at IBM Research, we also developed one of those tools. It's an Apache project now. It's called SystemML. I will not go into too much detail here in the interest of time, but if you go to systemml.apache.org, you will find our webpage there with a whole bunch of documentation. You will also find the links to the GitHub repository there. You can download it and build it. It's a Maven project. You can go to the Maven repo and download our latest releases and so forth. But the gist of it is really, it's not a GUI interface, okay, but we give you a language, a high-level language to implement your algorithm, okay, or your deep learning architecture. And then we have a compiler and a runtime optimizer that takes away a lot of burden from here in order to run it on a MapReduce or on a Spark cluster, or push the computation onto a GPU if your system has one. The system does all of that work automatically for you, without you having to go into your TensorFlow configuration file and say, okay, I want that layer over here and that layer over there. You will also, there's also in the GitHub repository, there's an examples folder there. If you go into this example folder, in there we have this one of the hello world examples from deep learning. It's this MNIST dataset. Does everyone know this MNIST dataset? Okay, most people do know it. But for the people who do not know it, it's kind of they made this dataset of 60,000 images available. It's 28 by 28 pixels of numbers between 0 and 9. So they all look like that, or like that, or like that. And the task is to train a neural model on it that automatically looks at this image, takes it as an input, and then it says, okay, that one is an 8, that one is a 3, that one is a 4, and so forth. That sounds like an extremely simple trivial example, but it actually can be very hard. Okay. People have been looking at it for quite a number of years. I could show you a demo, they developed this one neural model architecture that everyone uses now. It's called the Lunette with 5 layers. People are just taking that one in Keras or in our system. They train the 60,000 images on it, and you will get, I don't know, probably like a 96% accuracy on the correct prediction of those numbers.
So now you see the net.
The net.
So that is another net,
Another different.
just like
Okay.
ResNet.
I see.
Yes.
Yes.
Okay. So check out our repository, exactly that same. It's a Jupyter notebook. You will find it in there. Okay. So people may wonder, why is a SystemML? Why is a TensorFlow? Why is a PyTorch? Why is a big deal? And which one is better? They are all better. Okay. There is not a single answer to that question, and I will use this animation here to explain to you why is it so difficult to compare and say, this one is X% faster than the other one. So we took exactly this Lunette MNIST example with 60,000 images, and we just trained it on 10 epochs. 10 epochs means we went 10 times over the same data set in order to optimize for our function. Okay, and then we do actually performance comparisons. Okay, and question is, where do you run it on? Okay, do you have only a CPU, or can you also run it on a GPU? Okay, are you doing single precision, or are you doing double precision math? Okay. And depending on those answers, you will get different performance. Okay, so he took TF is a blue, and we took TensorFlow, and they have a switch in their engine that allows them, that they call accelerate for code generation, which gives a performance boost. Okay, but it's not quite general yet. Okay. And then we also took our system, which is this color, SystemML, okay, with and without code generation. Okay, and then we took another one, big DL from Intel. Okay. It's a sparse graph, okay, because we could not produce all the numbers. For instance, TensorFlow, they do not support double precision, they only do single precision. Okay, so if that is okay with you for your scenario, then fine, you don't need double precision, but you don't, then you have to live with single precision. Okay. For SystemML, okay, although we have GPU and CPU support, we also support single precision and double precision, but our code generation, we don't have code generation for the GPU, we only have it for the CPU. Okay. Hence, it's sparse in that space. And big deal, because it comes from Intel, they don't support NVIDIA GPUs, okay? So, sparse. Now, let's look at the ones that we have here. TensorFlow is doing very well, okay, for single precision on a CPU, and it's doing better than our system, and that is the case because also SystemML does support single precision, but it's not general. It's not really baked into the engine, so there is still some conversion happening between single and double precision, and of course that costs performance. Hence, we do not do it as well there. SystemML as well as TensorFlow, they outperform big deal for mini-batch processing. Okay, but if everything comes together to kind of the same scenario, okay, then actually the performance is equally good, almost. Okay. Why is that the case? Because if we all go to the same GPU, okay, and we use the same CUDA or cuDNN kernels to do the computation on it, and we agree on single precision, then we just invoke all the same code, so then the performance should be the same. Okay. But it's quite complicated, and it's not a straightforward answer to say one is better than the other. It's just impossible. Okay, I'm gonna skip that one here. In terms of hardware and chips, same thing there. It's a very complicated story. There's just not one chip to rule them all. If you have to choose your hardware, okay, ask yourself the question, what do you want to use it for? Do you want to use it for training or for inference? The difference typically is for training you want to optimize for throughput, for inference you want to optimize for latency. Okay, that makes a big difference. Typically the TPUs and the FPGAs, they say they're better for inference. Okay, so that's why you see here the GUI TPUs as well as the FPGAs. Okay, but for training, it's a slightly old slide, so it's actually now already here. The next one, P100, is the V100. And then Intel also always has a little, for edge computing, for the edge devices, you have the little sticks, the neural sticks that you can actually use for inference at the edge. Okay, I think that's almost the last slide that I have. You don't have to go through the details of this one here, but the high-level message is really to say just choosing the best chips, that is not enough. You really have to look at the overall system design. Okay, and system design also means like choose good chips, but the memory bus is equally important as well as the memory speed. Okay, and the connectivity between the CPU and the GPUs. Okay, so NVIDIA has this NVLink that definitely outperforms by orders of magnitude the PCI connectivity that Intel typically has to use. And on power we have the NVLinks and the cap. Okay. There's more information. Check out our Research AI website. here's a link to the Watson Studio, and if you are interested in checking out our research prototype, go to our project.org and take a look.